when we are looking at a differential equation for which the residual is a pretty weird thing. It's a delta function plus an arbitrary function. So now let's write down the definition of projection. I mean the alternative definition of a projection. Operate on this one. That means an integration. That means the inner product of this residual with any delta G has to be 0 for any delta G within XH. Or if I write down the inner product in a more mundane way, it's the integration of this times delta G dx has to be 0. Okay, we have no idea what, I mean, this is a weird thing, right? It has delta functions in it, but delta functions is not a normal function. It is only defined as a convolution without the functions, right? So we are happy with this, because even if the second order derivative is delta functions, we are looking at the formulation as a convolution of this delta function without the functions, with delta g's. So we are perfectly happy. Another way to make us happy is that we can actually get rid of the second order derivative here through integration by parts. Okay, integration by parts is actually application of something we used extensively in finite volume. It is application of the divergence theorem, okay, in finite volume. I mean, remember in finite volume, we use divergence theorem to convert an integral of the divergence of the flux into a boundary integral of the flux times the normal at the boundary, right? If you apply the divergence theorem in 1D, I mean, in one dimension, the divergence theorem just says integration from L, let me just say from 0 to 1 of partial, let me see, partial, I don't want to FGH, partial H, partial, okay, I need a function, eta, right? Eta, partial X, dx. In 1D divergence theorem, it's just equal to eta 1 minus eta 0. That's easy. That's divergence theorem in 1D is too easy. It's almost too easy. Now in this case, I'm going to define eta being delta G times partial UH partial X. Okay, or integration by parts, basically plugging this eta being a product of two functions. If eta is a product of two functions, then partial eta partial X is also going to be the summation of two terms. It's partial delta G partial X times partial UH partial X plus delta G times the second order derivative of the the UH. That's just chain rule. And then integration from 0 to 1 of this term is exactly what we have here. So we can exchange this to a boundary term minus a term that only involves first order derivatives. Okay. Or if I write it over here, integration from 0 to 1 partial square UH partial X squared times delta G is equal to eta over 1 and H, and eta is delta G times partial U partial X 1 0. Ooh, sorry. Okay, minus integration 0 to 1 of this guy, partial delta G partial X times partial UH partial X dx. now basically we got rid of the second derivative term, and we only have first order derivative of delta G and UH. We know that both delta G and UH are piecewise linear and continuous functions. So the first order derivatives of both functions are perfectly well defined. It is the same as applying these delta functions to the delta G. All right. So this is what we mean by projecting a differential equation into a finite dimensional functional space. Okay. It is so by doing this, we get the finite element solution of this differential equation. The finite element solution is a function within a prescribed finite dimensional space, which makes the residual of the differential equation to be as close to zero as possible within the same functional space. Okay. Well, I said the same functional space, but like that's actually a subclass of finite element methods called the Galerkin method. The Galerkin method is using the same space for approximating the solution and for the projection. There are some other methods that uses different space for approximating the solution and for this projection operator. But like in most for most differential equations, we are, I mean, for most well, for many differential equations, we are very happy just using the same space for approximation and for projection. So that.
Come on. Okay. All right. Okay. What time is it? Okay. So let me elaborate a little bit more on the Poisson's equation. Okay. So we did the projection, but it is still not perfectly clear how to solve it. And let me actually get to the end of the closed loop on the Poisson's equation and make sure we know how do we solve it. So if you look at this equation or the equation after the integration by parts, whichever way is it doesn't matter. If you look at this equation has to be true for any delta G within XH, right? This equation is not just one equation, it's a set of infinite number of equations. But are these infinite set of equations independent from each other? No. Yeah, because if I know this equation is satisfied for one particular delta G, then I know this is satisfied for 2 times delta G, right? So this equation is, if I perform any linear combination of this equation for different delta G, it is still going to be satisfied as long as the components of the linear combination is satisfied. In other words, if I can find a set of basis functions whose linear combination can represent any delta G, then I only need to enforce this equation on this basis in order for this equation to be true for any delta G. So instead of writing this equation for any delta G in the obscure setting, let's write it to be more explicit. We just need, let me actually write it in the more, that's fine. We can just write this equation instead of for delta G, we write it for phi I of x dx for I goes from 1 to n, where n is the number of basis functions. So instead of infinite equations, we get a finite number of equations. That's good. Now what is missing? What is missing is we still have we want to solve for UH, and UH is a function. And we don't want to solve for functions, we want to solve for numbers. That's what computers can do. Computers can only deal with numbers, it can't deal with functions. So what's left?
Solution approximation.
Yeah, we want to represent this UH with numbers. And how do we represent UH with numbers?
Linear combination.
Linear combination again, right? So we are going to write, we know that UH, because it's in the same space of XH, we are going to represent it as a summation from 1 to n, an times ai times phi of x. Great. Now, these are the unknowns because all the phis are known, right? So basically what we have is integration, and let me write this as j because I don't want to conflict with the I here. So integration from 0 to 1, and I can actually pull this summation out because aj's are just stuff. Integration of aj, partial square phi j of x, partial x square phi I of x, right, dx, plus integration f times phi I of x dx, fx is equal to 0. I mean, this is equal to 0. For I goes from 1 to n. We have n equations, n unknowns. We can solve for them. And it's not surprising, this is a linear system actually. If you look at this, if you define this as, okay, let me define this thing as bi, right? For each basis, for each I can take whatever function is. I don't have to approximate it using piecewise linear. I can take whatever f is. I can integrate f with one of these basis functions, right? That gives me a particular component of this n-dimensional vector bi, right? So by doing this, I can get b1, etc., bn. I can also look at this. This has an I and has a j. And I can do this for different I combinations of I and j. Alright, this gets me a matrix Aij. Right? Any problem on that? Then the solution a1 to an is equal to a backslash b, right? I'm done. I solved the Poisson's equation.